welcome to this explainer. So if you're navigating the world of computer science, maybe studying for exams, or gearing up for those notoriously brutal technical interviews, you've absolutely encountered the classic dilemma of how to store your data. Well, today we're going to completely demystify this showdown between arrays and linked lists. We'll break down the foundational concepts, map out their hidden mechanics, and give you the ultimate mental models so you literally never confuse the two again.
All right, let's dive right in by asking a pretty fundamental question. When you sit down, write a program, and hit run, how exactly is your information organized in the computer's memory? It's easy to think of data storage as just this magical black box, but the reality is that the physical layout of your data dictates everything about how your software is going to perform. Choosing the right structure is kind of like choosing the right foundation for a skyscraper.
Here's our quick roadmap for the explainer today. We'll start with the ultimate data showdown. Compare a cinema to a treasure hunt, run an access speed test, look at modifying data and size, and finally, deliver the final verdict.
Okay, Section 1, the ultimate data showdown. Setting the stage for memory management. Arrays and linked lists are basically the building blocks for almost everything else you're going to code, so mastering their differences is absolutely crucial. Moving right along to Section 2, cinema versus treasure hunt. Visualizing the layout. To really grasp these structures, we need to map these super abstract technical concepts directly to everyday real-world scenarios. Let's look at the array first. An array places its data in contiguous or continuous memory blocks. All that means is every single piece of data is sitting directly next to another one, shoulder to shoulder, in a strict, unbroken line inside your computer's memory. Literally no gaps at all.
This brings us to our first analogy, a row of seats in a cinema. Think about it. Everyone sits right next to each other in a continuous line, and because of this rigid structure, finding a specific location is a breeze. If you want to find seat number 5, you literally just walk up to row 5 and boom, there's seat 5. The absolute most important keyword to burn into your memory for arrays is contiguous.
Now, on the exact opposite end of the spectrum, we have the linked list. A linked list relies on elements that are totally scattered all over memory. They are not sitting next to each other. Actually, scratch that. They're completely isolated. But they are connected to one another via something we call pointers. Imagine a treasure hunt. Honestly, this is the perfect mental model for linked list. The clues are hidden in completely scattered places across the map. You don't know where all the clues are from the start. Instead, you find the first clue, and that piece of paper literally points you to where the next clue is hidden. It connects the scattered pieces together. Your key takeaway word here? Pointers. Section 3, the access speed test. How fast can you find it? Knowing the layout is great, but the next logical question is, how fast can you actually retrieve your information when your program asks for it?
Look at the stark contrast in speed here. Because arrays are perfectly continuous blocks, your computer can use simple math to jump directly to any item instantly. It just takes the base address, adds the index, multiplied by the size of the data, and you're there. We call this O of 1, or constant time. It is incredibly fast. Linked lists, however, well, they drag behind at a much slower O of n speed. Because the data is scattered, you can't use math to jump ahead. You're basically forced to start at the very beginning, the head, and traverse the data manually, node by node, until you finally hit your destination. So the big takeaway is this. Walking straight to your assigned cinema seat is virtually instant, right? The layout is mathematically predictable. But in a treasure hunt, you have to painstakingly find clue 1 to get to 2, 2 to get to 3, and 3 to find 4, all before you can even hope to reach clue number 5. That brings us to Section 4, modifying data and size, the agility round. Reading data is just half the battle. What happens when we need to dynamically insert new data right into the middle of our structure? In this agility test, the tables turn entirely. For arrays, insertion is painfully slow. If you want to drop a new element right in the middle of your array, you have to physically shift every single subsequent element down one slot just to make space. It's super inefficient. Linked lists, on the other hand, are blazingly fast here. Since the data is just scattered nodes connected by pointers, there is no shifting required at all. You just update the pointers of the previous and next nodes, and you're golden. Think back to our cinema analogy. The movie's already started, every seat in the row is taken, and you suddenly want to squeeze a brand new person right into the middle. What happens?
Everyone in that row has to groan, stand up, and awkwardly shuffle down one seat to make space. Massive disruption, right? That is exactly what an array has to do every single time you insert data in the middle.
Size flexibility is the other major differentiator. Arrays are completely rigid. They have a fixed size that you absolutely must declare right from the start. You declare an array of 10 slots and you suddenly need 11? Too bad. Linked lists are fully dynamic. Because they don't need a single continuous block of space, they can just keep growing organically, node by node, as long as your computer has free memory available anywhere.
To put that into perspective, if your array runs out of space, your only real option is to build an entirely new, larger array. Carefully copy all your old friends over to the new cinema row and abandon the old one. It's a huge chore. Meanwhile, adding to a linked list is as effortless as just grabbing a scrap of paper and scribbling down one more clue for your treasure hunt.
And we made it to section 5, the final verdict, the ultimate cheat sheet. Let's synthesize everything we've talked about today into your ultimate survival guide.
Okay, if you're prepping for an interview, I highly recommend you take a screenshot of this summary matrix right now. This is the gold mine. Knowing exactly when to utilize continuous, fast access memory versus flexible, scattered pointers is the absolute key to acing your test. Arrays give you that contiguous memory and lightning-fast O of 1 access speed, but you definitely pay the price with slow insertion and fixed sizes. Linked lists free you from those constraints with dynamic sizes and fast pointer-based insertions, but they penalize you with slow O of N search times.
So, as we wrap up this explainer, I'll leave you with this final thought. You now know the underlying strengths and those hidden weaknesses of the rigid cinema row versus the agile treasure hunt. When the time comes to architect and optimize your very own piece of world-changing software, which data structure will you trust to build your next big project?